Hi. So in this video, we're going to look at finding the roots of a polynomial with involving complex numbers. So the first thing we're going to look at is the fundamental theorem of algebra. There are three theorems which allow us to solve these polynomials. First one, if the root of a polynomial with real coefficients is non-real, that is of the form z equals a plus ib, then its conjugate z bar equals a minus ib is also a root. What that means in effect is that complex roots come in pairs. If you've got a plus ib, then you're going to have a minus ib. They're both going to be roots. Theorem 2, a polynomial of degree n will have n complex roots. Now remember, the definition of a complex number is it's going to have a real part and an imaginary part, so we can think of as any root as being complex. It's just that what we've dealt with before, the imaginary part has been equal to 0. So a polynomial of degree n will have n complex roots. The effect that this has is if the highest power in a polynomial is 5, so you've got x to the power 5 or z to the power 5 in terms of complex numbers, you're going to have 5 roots. If it's z to the power 3, then you have 3 roots. If it was z to the power 15, you would have 15 roots. And lastly, a polynomial of degree n with real coefficients can be reduced to the product of real linear factors and real irreducible quadratic factors. What that really just allows us to do is, using our knowledge of polynomials and quadratics, we can simplify the polynomial to its factors that are real, and then from the irreducible quadratic factors we can solve for the complex roots. So the three of them together allow us to solve polynomials for all roots. Okay. So first example, using the quadratic formula, find the two complex roots of z squared minus 4z plus 5 equals 0. Now, we've actually done this before for when we're doing differential equations. So if we remember that formula, z will equal negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, a is going to be 1, b is going to be negative 4, and z will be 5. Negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 5 all over 2 times 1. So z will equal 4 plus or minus the square root of 16 minus 20, because negative 4 squared is 16, 4 times 5 is 20, which is negative 4, all over 2. We now know, if you remember, that I squared equals negative 1. So I can rewrite this as 4 plus or minus the square root of 4i squared over 2, which allows us to get 4 plus or minus 2i over 2, which means that z equals 2 plus or minus I. And now there you can see why we always end up with the conjugates being pairs of roots, because of the quadratic formula. So because z equals 2 plus I as a root, z equals 2 minus I as a root. Okay. So we'll move on to another question. For the cubic equation, z cubed minus z squared minus z minus 15 equals 0, z equals 3 is a solution. Find the remaining complex roots. So the first thing we need to do is find out what the quadratic is going to be that is left when we have z equals 3 as a solution. What would that solution look like as a factor? Z minus 3 equals 0 is a factor. Therefore, to find quadratic left over, you could do this in higher by polynomial division, by synthetic division, but what we're going to do is use algebraic long division. So I'm going to divide z cubed minus z squared minus z minus 15 by z minus 3. What times z gives z cubed? Z squared. Z squared times z gives us z cubed. Z squared times negative 3 gives me 3z squared. And now I can subtract. Z cubed minus z cubed is 0. Negative z squared minus negative 3z squared is negative z squared plus 4z squared, which gives me, plus 3z squared, which gives me 2z squared. Let's bring down the negative z. What times z gives 2z squared? Well, it's going to be plus 2z. 2z times z will give us 2z squared. 2z times negative 3 will give us negative 6z. 2z squared minus 2z squared is 0. Negative z minus negative 6z is negative z plus 6z, which is 5z. Bring down the negative 15. What times z gives 5z? Plus 5. 5 times z is 5z. 5 times negative 3 is negative 15. And they subtract to give 0. The fact that I've got 0 as a remainder means I've done it right. Okay. So now we've got no remainder, we've got our solution, so that means that z minus 3 is a factor, and that leaves us with z squared plus 2z plus 5 equals 0. And now that is just an irreducible quadratic, which we can then use our quadratic formula to find the remaining complex roots, where a equals 1, b equals 2, and c equals 5. So we get negative 2 squared minus 4 times 1 times 5 all over 2 times 1. 4 minus 20 is negative 16. Negative 16 will become 16i squared, and the square root of that will be 4i. So z equals negative 1 plus or minus 2i. Therefore, our final solution is z equals 3 and z equals negative 1 plus or minus 2i. Okay, another one. For the cubic equation, the 2z cubed plus 5z squared plus 8z plus 20 equals 0. Z minus 2i is a factor. Find the roots of the equation. Okay, so using our knowledge of the fundamental theorem of algebra, if z minus 2i is a factor, therefore conjugate is a factor. So let's think of it as z equals 2i, or it would be z equals 0 plus 2i, where 0 is just the real part. Therefore, z equals negative 2i, also a factor. So, in order to get the complex roots, what we need to do is find out what the factors look like. So we've got z minus 2i and z plus 2i as factors. What we're going to have to do is find out what they look like as a quadratic once multiplied together, because what I'm going to have to do is find out the quadratic that they give and then use algebraic long division to find out the remaining roots. Okay, so we're going to do z minus 2i, z plus 2i, and that gives us z times z is z squared. Z times 2i is plus 2zi minus 2zi minus 4i squared, plus 2zi minus 2zi is 0, minus 4i squared becomes plus 4. Because z minus 2i and z minus plus 2i are factors, when I multiply them, z squared plus 4 is also going to be a factor. Okay, so what I now need to do is algebraic long division by z squared plus 4. So I'm going to get z squared plus 0z plus 4 dividing into 2z cubed plus 5z squared plus 8z plus 20. What times z squared gives 2z cubed? 2z. 2z times z squared is 2z cubed. 2z times 0z is 0z squared. 2z times 4 is plus 8z. 2z cubed minus 2z cubed is 0. 5z squared minus 0z squared is 5z squared. 8z plus 8z minus 8z is 0z. And then we can bring down the 20. What times z squared equals 5z squared? It is 5. 5 times z squared is 5z squared. 5 times 0 is 0z. And 5 times 4 is 20. Minus them, and that all comes out to be 0. No remainder. Therefore, I've done it correctly. Z squared plus 4 must be a factor. Now we look up our solution. That also means that 2z plus 5 is also a factor. So that would mean that z equals negative 5 over 2. Therefore, solutions are z equals 2i, z equals negative 2i, and z equals negative 5 over 2. Or if we had them written out as their factors, z minus 2i, z plus 2i, and z plus 5 over 2. Or 2z, or 2z plus 5. And that's the solutions. Okay? One last one. Show that z equals 2 plus I is a solution to f of z equals z to the power 4 minus 2z cubed minus z squared plus z, 2z plus 10. Hence, find all the remaining roots. Okay? So what I can do, if this is a solution, if I substitute it in, it should end up as 0. Okay? So, we're going to end up with f of 2 plus I will equal 2 plus I to the power 4 minus 2 times 2 plus I cubed minus 2 plus I squared plus 2 times 2 plus I plus 10. So I've substituted in. So we're going to end up with 2 plus I squared times 2 plus I squared. There's a reason I'm doing this. Minus 2 plus I squared 2 plus I minus 2 plus I squared plus 4 plus 2I plus 10. Split up into the 2 plus I squareds, because what I'm now going to do is find out what 2 plus I squared is. Think about 2 times 2 will give us 4. 2 times I plus 2 times I will give us plus 4I. And then I times I will give us I squared, which is just minus 1. So we get 3 plus 4I. So 2 plus I squared is 3 plus 4i. Four plus 10 is 14. 3 times 3 is 9. 3 times 4i is 12i. 4i plus times 3 is 12i. 4i times 4i is 16i squared. 3 times 2 is 6. 3 times I is 3i. 8i, 4i squared. Minus 3 plus 4i becomes minus 3 minus 4i plus 14 plus 2i. So we've got 9 plus 24i minus 16, because I squared becomes negative 1, minus 12 minus 6i, minus 2 times 8 is minus 16i. The 4i squared becomes negative 4, and then the negative 4 times the negative 2 becomes plus 8, minus 3 minus 4i plus 14 plus 2i. Now we can combine all the real parts and the imaginary parts. So 9 minus 16 minus 12 plus 8 minus 3 plus 14 equals 0. So the real parts equal 0 so far. Now let's do the imaginary parts. 24 minus 6 minus 16 minus 4 plus 2 equals 0. Therefore, z equals 2 plus I is a solution. Okay, now remember our conjugate rule. If z equals 2 plus I, a solution, z equals 2 minus I, also a solution. Okay, so remember from the previous question, I need to find out what they look like once multiplied together. So we get 2 plus I, 2 minus I will equal 2 times 2 is 4. Nope. I need to do z minus 2 plus I, as in the actual factor, and z minus 2 minus I equals z minus 2 minus I, bracket z minus 2 plus I. So what I've done is I have converted them into their factors, as that's actually what we're going to divide by, and then we multiply them out. So z times z is z squared, z times negative 2, z times I, negative 2 times z, plus 4, minus 2i, minus iz, plus 2i, minus I squared, gives us z squared minus 2z, plus iz minus 2z plus 4, minus 2i, minus iz plus 2i, minus I squared, iz and minus iz, minus 2i and plus 2i, they all cancel out, and so we're left, and then we've got z squared minus 4z plus 4 plus 1 equals z squared minus 4z plus 5. The plus 1 has come from the negative I squared becoming negative 1, so it's negative negative 1, which is plus 1. And then we've got the quadratic that we can now divide the original equation by. So it's going to be z squared minus 4z plus 5 going into z to the power 4 minus 2z cubed minus z squared plus 2z plus 10. What times z squared is z to the power 4? Z times z squared times z squared is z to the power 4. Z squared times negative 4z is minus 4z cubed. Z squared times 5 is 5z squared. Z to the power 4 minus z to the power 4 is 0. Negative 2z cubed minus positive negative 4z cubed is negative 2z cubed plus 4z cubed, which is going to be 2z cubed. Negative z squared minus 5z squared is negative 6z squared. Bring down the 2z. What times z squared gives 2z cubed? 2z. So we get 2z cubed minus 8z plus 10z. 0, negative 6z squared plus 8z squared is going to be 2z squared. 2z minus 10z is negative 8z. And bring down to 10. What times z squared gives 2z squared? 2. And so we end up with 2z squared minus 8z plus 10, which makes 0. No remainder, therefore we've done it correctly, which means that our remaining quadratic is going to be z squared plus 2z plus 2. And we can solve this now, as actually that is a factorizable quadratic. Therefore, z equals negative 1 and z equals 1. So now we've got our 4 solutions, which we knew should have happened because it was a z to the power of 4. And they are z equals negative 1, z equals 1, z equals 2 plus I, and z equals 2 minus I. If that turned out to be a complex solution, as in it is not solvable, all we'd have then done is use the quadratic formula. But in this case it was 2 complex roots and 2 real roots. However, it could just as easily have been 4 complex roots. Okay, so that is how you solve for polynomials complex roots. And again, a nice 23-minute video.